Hello all, welcome to the Linux Rootkits for Red Blue Teams course on Pentester Academy. Now in this video, we will continue our exploration into process information and look at how we can figure out the binary executable and other associated paths of a given process. Now what we've seen so far in previous videos that the task struct, which is what internally is representing the process, or rather the thread, has the COM member in it, and the COM member unfortunately has a size limitation of around 16 bytes. So as we found that when we try to print out this field, most of the time it ends up getting truncated, and hence we aren't able to get the executable name most of the time, right? Now, even if we did somehow manage to get the executable name, keep in mind that, we still don't know the exact path, right? There could be executables with the same name but in different paths. So we still don't know where this executable was picked up from. So the whole idea of this video is to try and demystify this problem. Now, do not get intimidated. The solution is actually pretty simple, and will also illustrate one of the things we would have to do more often than not in the kernel, which is jump through a lot of interconnected data structures in order to find the information that we are looking for. So what we are going to do is, inside task struct, there is actually another member which is a pointer to an struct, and is really memory map. And that memory map structure, which is actually mapped to, which is contained in every task, internally contains another structure called struct file, which stores the reference to the actual exe. Now it's important to note that the struct, the member, is only valid for user mode processes, right? Kernel threads have this value set to null. Now, assuming for user mode threads, we have found out the value, and inside the structure, we actually figure out the struct file, which is what basically points to a data structure with information about the exe file. Now, if you looked at the file structure closely, you would actually find inside that there is another structure called struct path with the name f_path. And this structure is what we are going to use to find the actual exe file name, including its path. Now, in order to go ahead and get the whole exe path, what we do is feed this value into a utility function called d_path, which finally gives us the entire path with the executable name. Wow. So let's actually jump right in and explore all of these structures. So here is my kernel directory, and I'm going to quickly go ahead and open up the file we've already looked at, Linux shed.h, and the task structure is what we are interested in. Now if you actually go down below, we would find that this contains, as I said, a pointer to a memory map structure called Now if we try to look at the structure, what you would find is, inside the structure, if we scroll down, we actually have another structure inside that called struct file, which is basically what is pointing and storing a reference to the file. Now, if you want to look at the file structure, so sometimes, as you can see, C tags ends up indexing it the wrong way. So I'm going to use cscope really quickly and try to look for a global definition for file. Should be in a file called fs.h, but let's actually find it here. Here it is, fs.h. What you'd find is that inside that you once again have another structure, struct path, and the value is f underscore path is the name of the member. And this is what we are actually going to use. And again, this is going to go and now look at a lot of other stuff at a low level to figure out the actual path. We don't need to get down to this level. But this is what we are going to use to go ahead and find the path. So in order to find the path, there is a utility function d underscore path. And you can see this basically says returns the path of a D entry. And basically we feed in the path, which is what we receive from all of that pointer magic. And after that, we also feed in an input buffer and an input buffer length. And inside this, the return path would be held. Now, a word of caution, when this returns, it might not basically begin from the very start of the buffer. It can actually begin from anywhere in the buffer. And that is where this function actually returns a pointer to that location within buff from where the path, including the exe name, actually begins. Okay, fantastic. So now let's actually look at the final code. And again, as I said, I'm not going to type things out, doesn't make any sense. So let's actually jump into the code. So what I've done is inside process underscore library, I've actually written a very simple utility function, process task binary name, and that takes a task structure as input. So we've kept it extremely high level so that if you want to use this in your programs, it's quite abstracted out, right? All you have to do is pass a pointer to the task struct. Now here what we do first of all is of course check if the memory map is null or not. As I mentioned, if it is null, then what we figure out is this is in all probability a kernel thread. Now if it is not null, then we go ahead and read out the value so that we can print the actual path of the executable. Now to do this, it's kind of important. Keep in mind that most of these structures have a lot of moving parts and there could be, other threads which are actually trying to modify, change, and so many other things are possible, right? Especially on SMP systems. And even on non-SMP systems, keep in mind that, a process may be put to sleep temporarily by the scheduler. Rather, a task may be put to sleep by the scheduler and other tasks wake up, which may once again try to access common structures. Also at times, references are important, the number of active tasks which are referencing something. Anyway, so to make sure that we are doing this right, we need to go ahead and hold the memory map semaphore, which is basically located under the struct mm. And this is basically mmap underscore sem. We need to hold the memory map semaphore with read bias, right? And once we are done working with the structure, we are going to release it by calling upread. So we call downread to basically hold it with read bias, and we call upread to release that. Now, inside this is where the magic is happening. The first thing we actually check is that, the exe file substructure as we move forward, the struct file, that should be non-null, of course. And if that is the case, then first of all, we allocate enough memory to hold the return value of the actual path. Now, inside the kernel, there is actually a defined value path underscore max. And this basically defines the maximum length that a path name can be, including the final null terminator, right, which is 4096, as you can see here. So of course we want to make sure that we can hold the largest possible path with null included, and we go ahead and allocate that memory here. And of course, if memory allocation fails, it's better to put out a kernel panic. So the dreaded kernel panic. Now, assuming that we got that memory, all we do is now call dpath, pass in the f underscore path structure, and basically make sure that we pass in our buffer, which is temp underscore path, the maximum size, which is the size of the buffer, path underscore max, right? Now this will return a pointer which is pointing somewhere inside this temp path where the actual path of the executable has been copied out. So we go ahead and print it, and then we make sure that we free temp path which we just allocated, right? If you don't do that, there's going to be a memory leak. So, well, that's exactly how we go ahead and do this. Now, additionally, what we can also find is the task's current working directory and its root path. And the process is really very simple. I'm going to leave this as an exercise to you. But finally, after you locate the structure member, all you have to do again is just call dpath like we've done above. Okay. So now let's compile this program and see it running. So I'm just going to make sure it's basically, okay, probably one of my test programs which I just ran. So sudo, let's actually do a ps ax first. Let's find an interesting program. Oh, why don't we find our cscope program, right? See where it's located and all of that. So 33972. Okay. So first let's clear the dmessage output. And then sudo insmod pinfo part.ko process underscore ID is this value. Let's do a dmessage, and here we go. I mean, apart from all the information we already know exists, if you notice, the binary path is user bin cscope, fantastic. And the other two information as well, which is the root path, which is slash for this mounted file system, followed by the pwd path, which is basically home Vivek Linux 4.16.7, right? Which is really the directory where we have invoked this cscope, as you can clearly see here, right? Fantastic. So you can see we managed to get a lot of interesting information. Let's actually try to do it for one more process. Let's say, let's try to take something with kind of a long name. Maybe we can try one of these genome programs. So 2008, let's put this in. There you go. If you notice, this time around, we were able to get the entire binary path, right? GSD date time, which is really, I think, what was running here. Here it is, right? If you had used the com value, like previously, this would have been truncated somewhere about here, right? But now we are able to get the entire binary path. Fantastic. And again, we get the root path and the pwd path where this program is actually getting invoked. So this is really how we can go ahead and look at a running tasks binary file as well as the present working directory and the root path. And this can be very, very informational, because keep in mind that if you're writing a kernel module to do a lot of low-level activities, dealing with tasks, which basically in user space is processes and threads, then to have the ability to figure out what binary was loaded and all of that is very, very essential. Okay, so I hope you enjoyed this video. I know some of this is going to be a little bit intimidating in the start, but once you start getting used to correlating all of these structures and figuring out how you can bounce around, pick up the right members and seeing if there are convenience functions, you'll actually see kernel programming is a lot of fun, right? So hopefully I'm getting you more and more excited. And well, try the code out. That's all I have in mind for this video. Thank you.